when you get into Nabari, you want to have it set up so that you are seeing this, this repo. You want to clone this repo. This is the one. There. And you should see the files, the directories image, part 1, part 2, part 3, and environment YAML, license and README. Go into part 1. And in each of these directories, there are slides that I'll show, a workbook that you open, and then there will be some some lecture parts, and in the lecture parts I'll show slides, and the workbook is for working out the little problems that I have throughout the slides. And then after that section, there will be a project, and you're going to spend some amount of time on it, something like 20 minutes. And then we'll go over solutions afterward. And then we'll do that for part 2 and then for part 3. The full schedule is down here, so you can tell me if I'm falling behind. I'll be checking the time also. And I hope I keep my voice. Oh, so everybody's ready. Great. And it's time, so let's go. And then whenever I do this, I can always just reset it like that. All goes back to 0. Yep. Okay. So starting into part 1, let's get going. So this is thinking in arrays. It's about array-oriented programming, and I guess I'll start by explaining what that is. So, what is array-oriented programming? So this is a programming paradigm alongside imperative, object-oriented, functional. Some of these paradigms are well known, like object-oriented was a big thing in the 90s. And some of them are less known, like actor-based programming or, React and such. This is one that is particularly useful in the sciences, so that's why we're here. So in array-oriented programming, the primary data type is an array, and most of the functions perform one operation on all the elements of the array, as opposed to performing one option on one element or something. So get started. We always import NumPy first. So for instance, this is not array-oriented. We have some input data. We want to fill an output array, and we're using arrays in both cases. But we write a Python for loop that explicitly says the order of operations. The computer would be doing this wrong if it started with the last one and worked to the first, because the programming language, the human-readable programming language, has said you must start at element 0, then 1, then 2, then 3. And then the user says what happens to each element. So these are things that you wouldn't find in, this is not very array-oriented programming. By the way, these paradigms are kind of like saying that something is or is not Pythonic. It's kind of a loose term. There. So here's another thing that is not array-oriented, although it is a little bit closer. You start with an input array, and then you create the output array in a single statement. This statement, well, it does NumPy from iter, because what we're writing down here is a Python iterator. And this iterator maps a function onto the data. So for each data element, this function gets computed to produce the output data. This is Well, at least it's doing everything in one statement. But this is functional programming because we're still focused on individual elements, x. This function is a function of an individual element. And array-oriented programming generally doesn't do that. Generally, it doesn't do that. It doesn't, yeah. So here's array-oriented programming. You have an input array, and you produce the output array with this one statement that is, this one expression actually. This operation squared, you write it once, and it applies to every element of the array. So this is what we're talking about. And you actually, maybe like show of hands, for how many people is this kind of code very familiar? Yeah, right. We'll be doing more in-depth examples than this, just so you know. Okay, so as with all programming paradigms, there isn't a sharply defined rule that cleanly separates between them. You can find people using the word functional programming to mean slightly different things. Same thing here. They're styles, and they're useful because each brings different programming concepts into the foreground. So maybe all of these programming concepts are relevant, but some programming styles highlight others some at the expense of others. So, imperative procedural really focuses on low-level algorithms, and if you're interested in low-level algorithms, you probably want to be writing them imperatively. Object-oriented focuses on large program structure, et cetera. And array-oriented, the focus is data distributions. And since in the sciences we are interested in statistical ensembles of distributions most of the time, we find ourselves doing array-oriented programming most often. So what is it good for? To start to answer that question, I have been collecting just like what are the array-oriented programming languages and what have they been used for in the past? And this plot has been getting more and more crowded as I find out about more and more obscure array-oriented programming languages. But you'll find that a few of them in there are things you might have heard of. Matlab is in there. S and then its successor R. R is a very array-oriented programming language, in addition to being fairly functional as well. Fortran 90 is hidden in there because it has some array-oriented techniques, but it's actually quite a bit different from all the rest in that it's this precompiled language. NumPy is there. Julia is in here at the same level as Fortran 90 because it has an operator that turns scalar operations into array-oriented operations, and so it qualifies. And there are some very recent languages. Dex is part functional, part array. XND is not something that humans usually write, but it's an array-oriented backend. And awkward array, which we'll be talking about in the third section. And then the observation is that most of these, including the ones that are obscure, are intended as interactive data analysis environments. Fortran 90 is, in fact, the only one that isn't interactive. It doesn't have a prompt. Although, actually, there are people working on that, like a REPL for Fortran. Most all of them feature an interactive REPL, and by REPL I mean read, evaluate, print loop. Concise notation, and they're unabashedly mathematical. They're intended for people who are who want to see mathematical notation because translating into some other form would be a burden rather than the other way around. The oldest of them all, the grandfather of this, is APL, which it seems like it really ought to have stood for Array Programming Language because that's very much what it is, but it stands for a programming language because this is so early on that they felt they didn't need to qualify them. It uses weird symbols throughout, so they had to have special keyboards in order to use this language. But this was also at a time before keyboards were standardized, and it was before ASCII. So it's a lot of room to do that. So the first exercise is going to involve writing a little bit of APL, just to just to get a sense of what this is like, because this has all the concepts in it. Yeah, I should have had a plan for myself of what to calculate, but let's do something like this is how you would make an array from 1 through 5. Although you can also do it with, where's the iota? There's iota. Iota 5. There. You can add two arrays. Let's see. Can I do it? Help, please. Yeah, okay, you put it in between. Plus. Like that. You can reduce an array, and the reducing is actually a bit like Julia having a special operator for it. This plus was the same thing when it was a plus as a operator between two arrays, and now to make it a reducer, to reduce an array, just put a slash. 1, 2, 3, 4, 5. Maybe I need a space. I don't know. So that reduces 1, 2, 3, 4, 5 to 15, which is the sum of 1 through 5. So, first Quizlet is to translate the following NumPy operations into APL. So, NumPy A range gives you a list from 0 to 9. For A range 10. The sum adds that up. I've shown a little bit of this. And the cumulative sum is like a variant of the sum, where it makes an array that has all of the cumulative results as you're adding these from left to right. Okay, it's been 5 minutes and 90% are done. So let's look at this. Oh, more people have started. Is it just starting now? Okay. Well, there will be more exercises as we go on. So I'll start by, okay. For these exercises, the first one, A range, was similar to the iota that I showed, except you see that this iota started counting with 1, because it was some years before we learned that the right true way to index arrays is starting with 0. I feel very strongly about that. And I feel like it's more than an opinion, but it's not something to go into now. In order to get this to start with 0, just to make it more like NumPy, I mean, it would have been fine if you started with 1, but to make it start with 0 is what I would do. Okay, that wasn't right. Let me fix that. Parentheses do work in this language. There, that does it. The second one was a summation of that. Copy. And I was already showing that if you take the plus operator and slash it, it becomes a reducer. But then I realized after the fact I should give a little bit more of a hint that reducing and scanning are kind of like opposites. And so APL treated them by having the slash go the other way. Then backslash. And that is the scan. So this is the sum up to the first element is 0, sum up to element 0 is 0, sum up to element 1 is 1, up to element 2 is 3, and then when you sum up to the last element, you get to the 45, which is the reduction. Okay, so this is not a course in APL. I just wanted to show that to get, to give a sense of, generalizing from the NumPy, Pandas, xarray that we're familiar with, kind of where this comes from and how far it generalizes and where this can go. Also, when we are looking at NumPy, being less concise than the originator, the first language was in fact more concise than the languages we're using now. It's because, oh yeah, so here's some solutions. This is what I went over in the previous slide, is that they started concise. It was clear from the beginning that they wanted to be concise in order to, focus their thoughts on the mathematical statements. But there's a problem with being too concise, because what APL programmers found is that after spending all night working on something and getting it to work, is crystalline, and they would never want to change it because it works because it's this very careful indexing thing that you put on a T-shirt. And so there's a T-shirt. Somebody was very proud of their program. I don't know how many days they spent on that, right? That was an achievement, so it was worth a T-shirt. So, where we're going to be going with this is that this is really about distributions and interactivity. With the array programming languages, these are the two things that are most important to us, the reason why we use them. So array-oriented languages bring distributions into the foreground. So let's start with a histogram library. I had originally planned to do more with this, but really I'm just using it to have small, not very large plots. 1 million data points. Oh, actually, some of the problems use the histogram library, so this is worth knowing about. This is an array-oriented histogramming language, histogramming library. So we start with a large data set, random numbers, 1 million of them, and because we're using modern computers, 1 million is nothing. 1 million is a megabyte, and how big is a megabyte? So questions that we can ask at any point is, how are the data distributed? The weird syntax with the histogram library is that we want a histogram binned with 100 bins from -5 to 5, and we want each of the bin values to be double, to be a single double. You can put weird accumulators in here, but we're just going to be using normal histograms, so that's a double. And then we fill it with the data set, and there it is. There's the distribution. They were Gaussian normal random numbers. If we use a different routine, we would get a different shape, because the shape of the statistical distribution matters. So what happens if we apply some function, like squaring every element? We can ask that by performing one operation and then looking at the plot again. Whereas if this were an imperative language, we would have to set up a for loop, which is possible, but it's more cumbersome to get to the immediate answer which we want, which is, if we did that one operation to every element in the array, what does the distribution look like? Also, with functional programming, we'd have to set up a function. We'd have to make a lambda and blah, 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 blah. This is really the quickest, most concise way to square every value in an array. And then what we see with that is that, okay, now they're all positive. They have this different distribution from Gaussian. Then what would this distribution look like? We take the last one. We take a reciprocal. We put that through the sine function. What would this distribution look like? I can't guess. That's, we have some complicated distribution. And that's what it turns out to look like. Goes from -1 to 1 because of the sine function, but then it has this, accumulation at the endpoints, and the positives are more heavily weighted than the negatives for lots of complicated reasons that if you were doing some statistical analysis, this all is the important thing. And having the computer be able to immediately show you, step by step through a formula, what does the distribution look like as you walk through each operation in a formula. Like if you wrap all this up in a script and don't look at anything until you run it, then you're not really harnessing the value that comes from array-oriented programming. So there's kind of two things here. The human readability advantage, the thing that you would lose if you put it all in a script and don't look at anything and just run it, is that the mathematical expressions are concise and more convenient to type interactively. And then, okay, yes, there's also a computational advantage, which you would still get if you put it in a script and run it, is that those loops are computed in a compiled, on the compiled side. And so it iterates over the loops much faster than Python could iterate over the loops. So there's a computational advantage. But I would zero in on this because there are faster ways to compute things by JIT compilation and such. The computational advantage is that the right part of the computation is accelerated, the loop over all values in the distribution. So it minimizes your wait between one plot and the next plot, not the wait from the beginning of the program to the end of the program. Okay, NumPy. About 10 minutes behind, but we will catch up. So NumPy you are all familiar with. There was a show of hands at the beginning. And I felt that this was a pretty good summary of NumPy, this cheat sheet. You've got really, this is all the data types. There's one data type, there's the array. And then just, one-dimensional, two-dimensional, three-dimensional, that's configurations of this one type. Creating arrays, I/O to and from disk, inspecting metadata on your array, mathematics, so the basic operations, like we've been talking about, comparisons, aggregates, these are the reducers. Slicing is very important. And then miscellaneous down here. It's just sort of an overview of the kinds of things you expect to find in NumPy. And it wasn't originally sectioned off like this. Originally, NumPy was going to be just a part of the SciPy package. And it was really great that it was pulled out and made into this base library. So NumPy's version of APL 10, 20, 30 plus 1, 2, 3 is array of 10, 20, 30 plus array of 1, 2, 3. A little less concise, but that less conciseness is sort of, decades spent finding just the right balance of conciseness. Since all of the scalar-to-scalar operations and all the scalar-to-scalar functions in NumPy dot whatever are promoted to element-wise operations and arrays, any closed-form expression, like a formula, like something you would find in a math book, duck types between scalars and arrays. So if you can write this for scalars, like the quadratic formula, it takes A, B, and C as input, and does that formula. Anything you can do on scalars, it works exactly, this function also works exactly on arrays. So if we want to compute the quadratic formula with scalar values, we put in some scalar values, and there's the answer. If we want to compute it on 1,000,000 values in an array, it's the same thing. That's a useful thing for going back and forth because you can compute, you can run the same code on a single value and inspect that value, run the same code on an array, and then plot it. So now this point about performance. NumPy is not the fastest way to compute numerics in Python. And the reason is because the way that NumPy works is kind of like this. And I italicize similar because NumPy is able to do some fusing, which is the opposite of this, but it's roughly. So if you were to write out the quadratic formula pedantically, and for each one of these arrays, compute a temporary array of -b, a temporary array of the square of b, a temporary array of the product of 4 and a, and do it, line by line like this, and get rid of the ones that are no longer necessary. This is pretty similar to what NumPy does when it's walking through a formula. Every time it hits one of those operations, it makes a new array. Allocating all that extra memory in the in-between steps, copying the data into them, all of these have costs. It's just that none of these costs are nearly as bad as a Python for loop. So it gives the same result. I'm not even going to check. So although it's faster than Python for loops, ... This is actually computing. There we go. By and you should usually expect orders of magnitude. Factor of 10, factor of 100, depending on what exactly you're doing, how many intermediates there are. 6 milliseconds, this is not quite a factor of 1,000, factor of some hundreds. And then the difference between the quadratic formula and the pedantic quadratic formula is, 6 milliseconds, 9 milliseconds. We're really not going to be worrying about those little bits because NumPy is a bit smart about being able to fuse some of the operations. It's not quite as bad as that. It's just close. Meanwhile, there are other libraries that fuse the operations. And by fuse, I mean take all of the operations in that formula and make it so that you can compute all of the operations in the formula on one element before moving on to the next element, so that you don't have to have any intermediate arrays, and there's a lot less copying, and this is like the next level of performance. So NumExpr is actually a virtual machine, but it's a fast one. It's whenever you use Pandas and you put an expression in quotes, it uses NumExpr. So you might have used NumExpr without knowing it. It's hidden inside Pandas. Numba is a compiler that compiles imperative code. It'll take something that looks like actually a subset of Python. Some Python can be compiled, and its paradigm is imperative. JAX compiles Python, and its paradigm is array-oriented. But since this is a single formula, they look the same. And then just do the race. Your results will vary being on different machines, such as the Nabari instance will get different numbers than this. But one thing that we will see is that these 3 fused computations will be somewhat faster than NumPy, maybe by a factor of 10. So we got a few hundred by going from Python to NumPy, and we can get another factor of 10 going to compiled. And this one is a virtual machine, so this is 3 times faster. Numba is 6 times faster. I'm rounding a lot. JAX, see in a moment. Same thing. And your results will really vary. This depends on what optimizations it's able to take advantage of. JAX likes to go to all cores, and it's actually kind of hard to keep JAX from using all your cores. So this is an open field, whereas NumPy is really, well, it had cornered the thought space on how to do arrays in program. There's arrays in Python, but in recent years, there are others, and we're trying to pull that back together with the array API. For compiling things and using compiled code in Python, there's wide open. There's a lot of ideas. All of these different colors are different ways of going about getting compiled code into Python. And some of them have lived and died, and others keep going. So this is a big open thing. So back to promoting NumPy again. Back to yes, no, yes, no. The amazing thing is we can express so much with these precompiled routines. We don't need a compiler in Python in order to do quite a lot of stuff. So we combine these element-wise operations, broadcasting, slicing and such, to do great things. So the NumPy becomes more than a library. It becomes a mini language within Python. So here is another little quiz. We want to compute the size of the spaces between consecutive elements. OK, we'll have a quiz in a moment. Between each of these elements they each increase by 1.1. And here I'm combining slicing with a ufunc in order to do that. We want to find the difference between them, so we want to take all of these minus all of these. So the idea is that ufuncs always go straight through, and we can do things like slice, and then the straight through is not quite so straight anymore. And the little quiz is to compute the length of a curve defined by arrays x and y. And the formula for distance of one segment is square root of x squared plus y squared. And we want to know the length of this whole thing. So this is going to involve putting together more than just ufuncs, more than just a formula. Use Matlab. This is the curve that you're computing. But you don't actually need to know that it's this cool like Celtic knot thing. It's just these two arrays, the x array and the y array. Actually, let me help out by showing what x and y look like. That's x, that's y. Okay. It's been 5 minutes. Most of you are done. So let's go into it. Here is an answer. One way to do it. I've packed everything into this. Let's see, do I explain more? No. Okay. This is the same trick that we used before on the x arrays in order to find distances between them, because it's the distance between each x that matters. Distances between each y. This gets squared. This gets squared. Add them, square root, and then we want to know the sum across all of these segments. This much here is the length of one segment. No, this is an array of the lengths of all the segments. I could help out by doing this. Just remove the sum. So the lengths of all the segments, and then we want to know the sum of the lengths of all the segments. So this is just putting together a lot of different pieces. This is a normal kind of problem that you encounter a lot in science, and it makes use of quite a few things. It makes use of slicing. It makes use of ufuncs and reducers, which are the basic things. Nearly at the end of this tutorial, so I'll just at this lecture, and then we'll go on to the first problem. I just looked ahead. We're almost there. Do I want to do this at all? Oh yeah, that's a clever. So this is a cute another use of it, and instead of skipping it, I'll just do it quickly. Big endian to little endian conversion. That's in memory. You have the numbers are represented by bytes. Some machines consider one end of that byte string to be, those 4 bytes or those 8 bytes for the 32-bit integer or 64-bit integer. Some computers consider one end to be the most significant digit and the other end to be the least significant, and other computers are swapped around. There are functions for switching them. In fact, this switches it to make these numbers 1.1, 2.2, 3.3, 4.4, 4.5 to the wrong endianness. And when you get wrong endianness, it looks like that. And maybe quick show of hands, who's ever has ever been doing something in a problem, and maybe not because of endianness, but you see floating point numbers that look like that. Yeah, this. And sometimes it's because of endianness, and sometimes it's because of other things. But when floating point numbers go wrong, they go wrong like that. So let's, not doing this as a quiz, just as a walkthrough. Let's do this endianness swap by hand. First, let's get the raw bytes. So now we're looking at uint 8 for each one of them. You see that this array is 8 times longer than this one. It's because we're looking at all the bytes. Group them into groups of 8 because these were originally 8-byte sequences. And now we'll use some very clever slicing. We keep everything in the first dimension, and in the second dimension, swap them. So each one of these things, the order has been reversed. Oops. Flatten it again to get back to a byte stream, and then view it. And we've fixed the endianness by hand instead of, using the proper routine like a normal person. Just to show, when I saw somebody do this, like I had some problem with bit endianness, which fortunately now there's a function for that as well. When you see stuff like this and you think, yeah, that was really clever. I'm glad that I've seen that. But you can do these things. You can always, there's enough tools there to do just about anything you want. This one's not going to be a Quizlet. I'm going to cut it for time. Downsampling a curve. I'm just going to walk through it like an example. We'll be reducing in order to downsample this curve. This is a noisy data in here. No, showing a plot of noisy. I have to see it as a plot. It uses the fact that you can reduce under different axes. If you've got a 2-dimensional array, axis 0 will sum one way, and axis 1 will sum the other way. And you get different results, like with this 1, 2, 3, 4, 10, 20, 30, 40, 100, 200, 300, 400. You add them down, you'll get 1, 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4. If you add the other way, the sum of 1, 2, 3, 4 is 10, 10, 20, 30, 40 is 100, etc. So the noisy data looks like that, and you want to get, we're going to skip it. We want to downsample it, and we did this by reshaping it into groups of 10. So taking that noisy data, grouping them this way into groups of 10, taking the mean of each of one of those, and then putting it back together into the plot. That would have been an exercise, but instead, we're going to go to the first project. How do you find the first project? It is in the same directory. The slides that I've been showing, the workbook that you've been using to do these quizzes as you go along, there's a project and there's a solutions. Open the project. We'll do the solutions after. I have some time set aside to walk through the solutions. And since we're behind, maybe I will, not show, I'll show just the main solution and then not talk about variants. The project is Conway's Game of Life, and for this, I'm not going to talk through it. You will read through it. Oh, and also, I would really like everybody to do these in small groups. So to pair with your neighbors, groups of 2 or 3, because I don't know if we have an even number or an odd number. So, so scoot next to your neighbor, look at each other's screens, especially if one of you has not been able to log into Nabari or not been able to compute these. You want to look on with somebody who can and does. In the instructions, there's quite a bit about what to do about the edges. Consider that like a bonus. I was talking about the edges in order to put that to rest. That a basic solution to this that ignores the edges and lets the edges of the game board just always be 0 is fine. That's actually the first solution that I'll show. And then, no, that's the second solution. But for the sake of this exercise, because it is a legitimately hard problem, let me say that. Yes. If you ignore the edges and get to it, then success. If you manage to make the edges wrap around, even better. Okay, so I'm going to start going over the solutions now. Yeah. There are more problems. There's more fun to have. All right, so the general strategy That's going to be true of all the solutions. And if you want, open up the solutions notebook now, because that's what I'll be going through. But the general strategy is in the hint of the project, which is you have one array, which is the current state of the board. You want to get another array, which is the new state of the board. And in between, you want to have an array, which is the number of neighbors. Because if you had an array of the number of neighbors, so they're not Boolean, they're integers, it'll allow you to compute what the next one ought to be. So, getting the new world from the from the old world and the number of neighbors is not too complicated. In fact, it's written out in the hint. If you have, if for each element in the world that is on, if the number of neighbors is greater than 1 and less than 4, so you're ANDing all of those things together. I should make this even wider. Yeah, there. Yep. Then, well, this is an array of survivors. This is a two-dimensional array of survivors. And similarly, two-dimensional array of births. The new world is births or survivors. So now for the solutions, I'm not going to go all the way through it. I'll just do some of the basic solutions. So here I'm going to rebuild this because it's a new notebook. Yeah. Oh no, I'm going to have to do this smaller. There, okay. So a completely general solution, just to get this off the, off our chest, there is a NumPy roll function that, when we piece this together, we can use this to compute the thing. You didn't have to just know about NumPy roll, because that feels like, oh man, there's just a function for this. So I'll show afterward how to do it if you don't know about NumPy roll. But let's take this. This is supposed to be like an anime eye, anime eyeball, kind of a, yeah, 1 bit. What roll does is it'll take this two-dimensional array and roll with a -1 here. We'll shift everything to the left, and it actually wraps around the edges. So it's a completely general solution. Look to the left, look to the right, look up, and look too far up, and it wraps around. And then, so given a one-dimensional array, this is for hint 2. Here we are with an example one-dimensional array, and we want to count left neighbors and right neighbors. This is like a one-dimensional version of the two-dimensional problem you're trying to solve. The left neighbors, you can get them if you roll it one way. See, the one is here and the one is here, and this is rolled in one direction. The right neighbors roll the other way, and the total neighbors is when you add them. So we could one-dimensionally get the left neighbors, get the right neighbors, and then add them to get the left or right neighbors. And so this is the total number of neighbors. And another tricky bit is that, we want to do this in 2 dimensions for all 8 possible rolls. In this 3x3 square, it's all the squares except the middle one, because it doesn't contribute to itself. So here is a completely general solution to step NumPy. You start by making a num neighbors a place to put this stuff, and then roll to the northwest, roll to the north, roll to the northeast, and keep adding, and keep adding until now num neighbors is really the number of neighbors in all 8 directions. You get the survivors and births, and then you return the new board. So this will do it. And let's just animate it. I think one thing I'm going to do is skip the timings. So I'm just animating, and there's the game of life playing out in this really high-tech animation. And with this particular starting point, it doesn't actually touch the edges. So that's how, it was arranged to not, if you have a solution that doesn't get the edges right, that'll be fine. It takes like 200 iterations before it gets around to where it would touch an edge. Okay. Yeah, and it's more than 10 times faster than the Python function. That's one of the ways of saying, look, this really is vectorized. So, you just have to guess NumPy roll. No, there's other ways to do it. Getting back to this one-dimensional example, we can do it with these slices. Take off the first one, take off the last one, and make left neighbors like this. Left neighbors is shifted here, and then what's in this 0 is something. I'm not going to get the edges right. Same thing for the right, but now the mystery edge is that one. And if we add these together, we'll get the right total number of neighbors for everything except the edges. So we could do it this way. And then this one, this is a solution that just gets the edges wrong. So here are the slices. To do the northwest, north, and northeast neighbors, we are slicing the first dimension, slicing off the first element of the first dimension, and the last element of the first dimension of the world. Imagine grids, cut off a thing, and like grid paper, think grid paper, and cut off one of the things and just move the grid paper. That's kind of the mental image to make here. And you can get all of the directions. In fact, you don't actually need to get the directions right because you're doing all of them except the center. So as long as you shift all combinations except for the middle one, you'll get it. And then this one also works. I need to reset the world. How do I do that? Is there a reset function? No, I forgot the reset function.
World equals new world.
What?
World equals new world.
Oh, yeah. I didn't exactly hear what you said, but let me do that. There you go. Okay. There. Oh, no, I need the initial state.
World equals new world.
New world. Thank you. Thanks. Now I've lost my place. World equals new world. Thanks. Okay. And then this one evolves appropriately also. So that's a solution that gets the edges wrong, but it's very simple. You can get the edges right. Not knowing about the roll function, you have to do extra work to do it. You can pad this, and if you pad it, then you can get the edges wrong on the padded version of it, but they're right on the not padded version. So that's a trick. Oh yeah, and did anyone attempt to use convolve? Great. Glad there was somebody. Because it turns out that a step in the game of life is actually a convolution. This is the convolution kernel. It's 111, 101, 111. So you could think of the game of life as an image, and you're applying a weird, convolver to it. If you think in convolutions, right? That's That's the way that you go about things. If you're like doing image analysis, this would be the way that you would probably approach a problem like this. And then the whole, this is a fully general solution. And it's not very many lines, but it's using the fact that you just recognize this as a convolution. And actually, that's an important point, too, that, like I said, this is unabashedly mathematical. You might, a big complicated solution can sometimes reduce down to a simpler solution if you notice some mathematical fact about it and know that there is a convolve function. But yeah, so we can also do that. I didn't import it. There. And there, SciPy is doing it. And I'm not going to go into which one's faster and whatever, because it mostly doesn't matter. It would probably be different on different machines anyway. They're all vectorized. OK, so let's move on. Good. OK. When you're doing this, you probably want to shut down your kernels so that you have enough memory on Nabari to go on to the next one. We go now into part 2. I'll do the slides. I think the workbook has nothing in it. Yeah, that's true. So I'll go through the slides. Try to keep a good pace so that you can focus on the project. Okay. So now, we've been applying array-oriented programming to formulas, which is kind of what it's meant for. That's the good, its sweet spot. Control flow is not its sweet spot. For control flow, by which I mean like if and for, that's kind of what imperative programming is about. So this, I'm going to be talking about the limitations of array-oriented programming. And yeah. So I'll start, I want to talk about single instruction, multiple data. You might have heard, actually raise your hands if you've heard of SIMD, if you've heard this word before. Okay, about half, well, or maybe less than half. So SIMD is a word that is often used for GPUs, because this is a GPU is a SIMD device in a way that a CPU is a, I think it's a SISD, single instruction, single data. No, actually, modern CPUs have both, but not to the degree that GPUs do. Modern CPUs have two kinds of registers. And now I'm getting really down to the hardware level, very low level. In the CPU, when individual bytecode instructions are happening on the machine, some of those instructions happen in registers that are large enough for a single number, and it applies a single operation on that single number. And some of them, some of these registers are big enough to hold 4 or 8, or maybe even 16 numbers. And that's a vector register in a CPU. And when you compile a program, it tries to auto-vectorize and tries to see, usually the programmer doesn't even see this unless they're a performance engineer and they get down into the details. The compilers try to get as much as they can onto the vector registers, because if they can get 8 numbers onto a vector register and apply one operation to update all 8, then that takes the time of one operation instead of 8 operations. GPUs are just like this, except they expose that multiple parallelism to the CUDA programmer or the OpenCL programmer. And they're much bigger, like 1024 instead of 8. So that's what, so let's do a simulation of them. Let me make registers in Python. And this is totally simulation. This is like, we're making a virtual machine in Python. Single register is a class instance. It's initialized by some value because we're going to put numbers in it. and then it has an operation add, and it adds the numbers in it. So this is how, scalar register is kind of almost doing nothing. It's just a wrapper around the idea that you can add numbers. A vector register is doing a little bit more. This vector register takes 4 values, and that's what it holds. And the addition operation on it adds each of those 4 values. So if you've got some raw memory, this raw memory array is RAM somewhere, list even. This is a Python list. In that RAM, you've just, there's some numbers that have been initialized there somehow. We'll grab some parts of this raw memory. So left is going to be these guys, right is going to be these guys. And here we're going to do some scalar operations. This is kind of simulating what a computer would do at the hardware level if you wanted to add the left array and the right array, and the compiler was only able to use scalar operations. It was not able to auto-vectorize the loop. It would work kind of like this. It would put a value into the register A, put a value into register B, and call the add operation on those registers to get the result. And that in each time step. And here's kind of what it does if it had vector registers. It would get a pack of numbers from this array, put them into one vector register, and actually that's all 4 of these. You would get a pack of values from the right array, put them in another register, and then apply one vector add to the vector registers, and it just computes the result in fewer time steps. And then caveats galore. Sometimes CPUs have to slow down to a slower clock rate in order to use the vector registers, and so whether it's better or not, these are all things that it's best to let the compiler decide it. But just, with a lot of hand waving, oh, look, it did it in 3 times less time. It's faster. So this is why people want to use vector registers. And then the drawback is that these instructions can only perform 4 operations at a time. These vector operations cannot just add one number, because that's how it's defined. And you also, here's where control flow comes into it. You can't decide whether or not to do the 4th addition based on the result of the 3rd addition. If you wanted to make choices like that, then you would really need to be using scalar operations. You'd need to do, compute through the 3rd operation, then have an if statement and say, oh, do I really want to do the 4th? So when using these vector computations, it's going to be more limited in what kinds of if statements and for loops we can do. Yeah. And then this is why you let the compiler do it, is because the compiler will analyze your program, see where, if you have if statements and for loops in the wrong places, and not auto-vectorize your loop. So if you're trying to get a compiler to vectorize your loop, it'll be a matter of saying, oops, I put an if statement here, I could have done something different. And that's how that normally goes. So I've been talking about that. This SIMD and vectorization, these are words for the hardware operation. In fact, I sometimes get in trouble when I talk about vectorizing a computation in NumPy if there's someone from, hardware community in the audience to say, that's not what vectorize means, except that in the NumPy world, we do use the word vectorize to refer to this because it is kind of the same concept. Array operations in libraries like NumPy, they're kind of SIMD. They're a single Python instruction applied to multiple data instead of a single hardware CPU instruction applied to multiple data. So yeah, we'll just be clear about what we mean. And whereas the hardware SIMD can be faster because it's doing fewer operations, the Python is faster because it's doing fewer operations in Python. Maybe it is just maybe the NumPy has been compiled without auto-vectorization, and maybe it is just scalar operations on the CPU. But the fact that we don't have a for loop in Python is already buying us a lot. It doesn't have to step through those Python statements. So we could call array-oriented programming high-level SIMD. It's Python-level SIMD. And it has all of the same conceptual limitations that SIMD has. So all of the things that would thwart hardware vectorization in SIMD, those same things would thwart high-level SIMD, NumPy. So I'm going to illustrate this by computing some special functions. Some special functions can be computed with just a formula, and some of them have to iterate until something converges. And that's where we're going to see this limitation. This iterate until converged is saying, do this step until the value is such and such. But that's putting an if statement in your control flow in what you want to do. So let's say that we wanted to compute this, and SciPy doesn't exist because, yes, there's a function for this in SciPy. There's a function for everything in SciPy. So, dust off numerical recipes. It's what we would use if we didn't have SciPy. And numerical recipes said that. I think my copy's in Pascal, so it said that in Pascal. It was implicitly scalar, like the numerical recipes is just defining algorithms to operate on scalar numbers. But this is going to work for arrays anyway because of, we can duck type between scalar and vector, between scalars and arrays. So this is the scalar version because here we have a Python list comprehension. And in this list comprehension, compute this log of gamma that I just defined on the previous slide. And a list comprehension is a Python for loop. It's right there. But that's the shape of it. And then we're just going to confirm it because with SciPy, I drew them on top of each other. You can't see the one because it's completely overlapped. SciPy gives us the same answer. All right, and now we can just run this, this function and pass in an array because scalars and arrays duck type. So we get the same shape. And NumPy could do this because every operation in this function is a closed form expression. It's a formula. It's like a mathematical formula. It might not look like it because there's this for loop here, but this for loop is really just a for loop over coefficients. It's computing a polynomial. This could have been written out as a long polynomial. Kind of the key thing here is that the thing that you're iterating over is a constant. It's not the array. And it's not something dynamic that changes in each iteration, each time through. So we could have written 6 lines that all look like this instead of having a for loop. So this for loop is benign. And also, like a compiler would notice that. A compiler would say, oh, yeah, I could vectorize that. OK, so now we're going to see a problem. Now we're going to see something that's not going to work. Another function. I'm just randomly pulling special functions out of numerical recipes. This one computes this particular integral, and I love the fact you can do LaTeX here, make that beautiful integral. This is what numerical recipes said to do. It said to write a for loop up to 100 times, because it really ought to converge after 100 times. And when it converges, it returns early from this function. And if it doesn't converge, well, that's a problem. So here's this function, and give it an array. And I can compute like a few of these. And there was I felt the time lag because there's these are list comprehensions. I was doing this all on scalars, passing Python numbers into this function. This is the same function with different parameterizations, 0.5, 2, and 10. And now we do it in SciPy. We get the same curves, because SciPy knows all of these things. But this one doesn't just work for arrays. If we try to put the array in, okay, show of hands, who has ever seen NumPy say the truth value of an array with more than one element is ambiguous? Yeah. Yep, comes up a lot. And it happens when you put a NumPy array into an if statement. Because, so this here, this absolute, so delta is an array, absolute delta is an array. Same thing for the summation and times small number. And then this less than is also vectorized. It makes this whole thing an array of Booleans, whether this is less than or not. It's an array of Booleans because for some values of the array, it has converged. For other values of the array, it has not converged. And Python wants to turn all of this into a single Boolean in order to know whether to follow this if statement or not. And NumPy says, well, we can't do that because it's not a single Boolean. It's a bunch of Booleans, and they're all different. It's making suggestions about using any and all because it thinks that might be what you want to do. But in fact, that is not what we want to do here. Well, maybe we could say all. Maybe we could have it jump ship when they've all converged. Yeah, so this says what I just said. So what should we do? There are kind of two solutions to this. One is to have all the values continue to iterate, even if they've already converged. It's just going to be chewing on 0, right? Just going around and around. This version of it, I just removed the if statement. It still loops over this thing 100 times. And if they've converged, if they've not converged, who knows? But we're leaving anyway. That's one solution. And with that, we can actually do this. This makes them iterate 100 times whether they're done or not. Or we could be really careful and keep track of which ones have converged and which ones have not converged. This involves more bookkeeping. So this is going to, what this is doing is it's applying the calculation only to the ones that have not converged, so we don't, quote, waste time computing things that have already converged. So this is the other solution. It also works. And it's certainly simpler to just forget about it, let them keep going, doing more computations than necessary. But now we'll have a race. Which one's faster? Oops. Well, since I already showed you. The answer will come up in just a moment. It turns out in this case, in this case-by-case thing, the easy one was faster. Letting it compute too much stuff made it some 5 times faster than trying to do all that bookkeeping. It's because there's a cost to the bookkeeping, you know, keeping track of which ones have converged and then putting all these slices to only apply the operations to the ones that haven't. And this is also true in hardware vectorization. Sometimes it's better to let unnecessary calculations happen than to spend your time trying to check which ones have converged or not. So now we're going to do the project 2, which is here it is. You should bring up projects from part 2. And like last time, I'm going to let you read this. Although I'll give a bit of an overview, even though there's text here. We're going to do an iterate until converged problem of walking decision trees. This is the kind of thing that really doesn't seem like you know, just, I picked something that I thought would be very odd to do in array-oriented programming. If you want to walk down a decision tree, and if you don't know about decision trees, it is explained in the notebook. If you want to walk down a tree, And it's just full of choices. Do you go left? Do you go right? You know, have I reached the end of the tree or not? It's full of choices. It seems like a really bad match to array-oriented programming. And that's why I chose it, was to show the limitations of array-oriented programming. But it turns out it's actually a good idea. And you know, in the solutions we apply, you know, doing a scalar like walking down the tree with, you know, compiled with NumPy, and array-oriented walking down the trees compiled with JAX. And actually, we win in the array-oriented case. So I was actually a little bit surprised that array-oriented programming even works for such ridiculously decision-bound things as walking down a tree. So I'll let you go at that. And again, pair up, make lots of noise. This is like where you get the most benefit from these tutorials, trying to work through these problems. Let's do this thing again. This, when are you done? Because I'd really like to know approximately where people are. So as a reminder of where to find this, on the GitHub page, there's a Slido link. Now it's 10:30. We'll go into the solutions. And I see that that actually not a whole lot of people have actually finished this one. And I understand that this is another legitimately hard problem, apparently harder than the last one, in fact. And just to give you a notion of what's coming, the third project isn't, the third project, Dask? Did we really going to do that? I don't think we're going to use Dask unless I'm remembering terribly. The third project is going to be not a hard problem. It's going to be similar to like one of the early Quizlets, but in a unfamiliar context. So this was the last hard problem, okay? Now, I think the really useful thing would be to be going through the solutions with all of this like primed in your brain. So let's do that now. So let's talk about it. First, I'm going to reevaluate the inputs so that we're back where we started, ready to compute things. Decision tree is going to be going to be modeling this difficult distribution. Let's scikit-learn make it. And this predict single is the scalar pure Python walk down the tree. It's what we would have in a computer science class, particularly like maybe a second semester, maybe first semester. Because in CS classes, we love to write recursive functions that walk down trees. I mean, that's like the best. And then there is the evaluated tree, which is kind of messy in here because it's this is an overtrained model, but that's not the point of this exercise. Is not having nicely trained machine learning models. The point is just having a tree at all to walk down, and then the fact that we can plot it, we can get a quick view on whether it's correct. So there's a discussion in the text was that you could do this in a purely immutable way, as in you don't change any arrays that have already been made. You know, you only make a new array, possibly fill it, and then after that it's set. And you use that, or you read from that array, but you don't rewrite into that array. And then there's a second version of it where you do overwrite an array. Another thing that I should say, sort of as a high level at the beginning, is that you know, I said that if statements and conditional while loops, loops that you don't know when you're going to break out of them, these are the things that are very hard for array-oriented programming. In a sense, you just can't even write those the way that you would write them in an imperative. The reason that we can walk through a tree is because all of these if statements are not control flow if statements in the program. They are data. You know, whether, you know, at each point in the tree, whether a particular datum in the tree goes through the left branch or the right branch is evaluating a value. You know, there's a value in an array that says go left or go right. And that's the sort of thing that we can apply across many Plinko balls, with all the Plinko balls falling down at the same time. One fixed tree, many evaluations of it, many things running through the tree all at the same time. And they're all in different parts of the tree. Every element of the array that's being passed through the tree is all in different parts of the tree, and all deciding to go left and right differently from every other element. But the choice between left and right is data. And then the other thing you need to worry about is iterate until converged. At some point you come to the leaves of the tree and ask to stop there. So we can have it spin its wheels. You know, it can, you know, the transition from an interior node to the next node depends on a value. Transition from a leaf to a leaf is, you know, it's always just spinning around, you know, keep coming back to that leaf. Okay. Right, so that's the general idea before getting into it. So, we have positions and array indices. And we're just going to be looking at what's in this decision tree. There's features. Oh, I made a little one. Yes, I made a little one. And this is useful. Make a little example to test things out on, because you need to look at partial results. Either you look at partial results by looking at a whole lot of them in a big distribution by plotting, or make the arrays small enough that you can see them on the screen. Yeah. Okay. Make a small array so you can see what's going on. And that small array has to have enough complexity in it that you see more than one decision being made. You want to see some things go left and some things go right. So we made this little one here. Made a little threshold. Okay. We're using the full tree. So this is going to the decision tree feature. So this is the full tree. And we just made a small array of positions. So these are the starting positions. And the array indices all start at 0 because we're starting at the root. Then the root is at array position 0. So going into one of these, like that, you know, we can get a scalar value. And by passing the whole array in the square brackets, we see what happens to each of them. So this is what happens to the 0th, this is what happens to the first, this is what happens to the second. We look at the thresholds here. We look at the children left and children right. So at first, they all see the same values because we started them all at 0, the root of the tree. And if I were to ad hoc decide that the first should go left and the other two should go right, here I've just changed that. Where do these numbers come from? 136. I'm not following my own text here. But the basic idea of what we're trying to do is get different results with different array indices. Well, that is happening. This got to 69, that got to 146. The basic idea of what we're trying to do here is use the thresholds, data values less than or equal to threshold will tell us, you know, is the value of this node yes or no? And yes goes left, no goes right. Right? So array-wise, does it have children at all is whether the left is greater than 0, because this is using -1 to say we're at a leaf. And the ones that will be choosing left are like this. Positions. The x values, we're going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, like that. And the y values are the features, the values of the tree node. And then we want to take that less than or equal to thresholds to decide whether we should choose left. So choosing left will be an array of Booleans. And if it chooses, and so then we just use those Booleans as a slice. What goes left, and everything tilde choosing left goes right. So here's a small example. Here's some positions. A range of positions, just to get indices that are going forward for the first dimension. Here are some features. And so here's what happens to the positions in that step. Other ways of slicing it. Just want to show that there are different ways of slicing it, and so that if you were following one path, you weren't wrong. A different one from the one that I showed. Okay, so then putting this together is NumPy where, which works like an if statement on a vector. NumPy where, here's the documentation for it. Give it a Boolean array, and then 2 more arrays, and it will give you the values from this array and the values from that array, depending on whether or not the corresponding value here is true or false. So the immutable version of this relies on knowing about the function NumPy where, which more so than NumPy roll, this is a basic function that's worth knowing about. The immutable version of this gets away with not knowing about NumPy where. Sorry, the mutable version, the other one, the one we'll do next. So we're not quite done because some of the nodes don't have children. The negative values for those left indices and right indices they have to go somewhere, because we can't, we want this to spin its wheels when it gets to a leaf. So we have to also have this question: do you have children? Is the left negative or not? And if you have children, then you're going to go to wherever you are right now. So there's this where for choosing to go left or right. And then there's also this where for if you don't have children, sorry about that. If you don't have children, you'll always go exactly where you are right now. So you build it up from NumPy wheres. So putting it all together, this is how to predict the next step. This is, we're starting at the root of the tree, and we want to go down to just the next level below the root. This function will do just that one step for all the values. Do you have children? Let's shorten the names of these things, more than shortening the names. Choosing the features for these array indices, wherever they happen to be, choosing the thresholds for these array indices, etc. And you'll often see a lot of code like this where there will be, you'll have a pack of arrays, like 5 arrays, that all have to work together. They all have to be the same length, and the elements of each correspond. So element I of one array corresponds with element I of the next array. And we're using that here. That's true of the features, thresholds, left indices, and right indices. And then we get the array of Booleans for choosing left. Should we go left or not depends on picking the actual values and comparing that to the thresholds to decide, are we less than or equal to the threshold for this node? And then we do that that where of wheres, so that, in the middle of the tree, we choose left when we're supposed to choose left and choose right when we're supposed to choose right. And at a leaf, we spin around. And that'll take us one step. If we repeatedly apply this function, we could walk all the way down the tree. And then the last problem is to know when we're at all the leaves, because we could apply that function infinitely many times, just keep going around, and eventually they'll all be at the leaves and spinning around, and we'd like to stop then. Okay, so this is a demonstration of the function, just going through one step. And you really have to stare at array values in order to follow that. I think what I will do is I'll move on. How many times do we need to evaluate the function to know when everything should stop? Actually, what I described a moment ago is maybe checking to see if everybody is in a leaf. Do numpy.all, or do what I did here, which is notice that this tree has a maximum depth of 10. So, if we go to the next step 10 times, then definitely they have all reached leaves. Maybe some of them have reached leaves before that, but it doesn't matter. We'll run it 10 times. So putting it all together, here's a predict many. This is a function that will walk down the whole tree simultaneously for like 1 million points, 1 million data points. He's doing it for just a small number of data points. And these are the final results. These are the decisions, orange or blue. Okay, let's make a plot with predict many. And we see that as the right shape. And it popped up a lot faster than the Python version. Okay, that was the solution for the totally immutable. That was, when we have an array, we make a completely new array with the results in it. And it relied on knowing about the NumPy where function. There's another solution to this where you take an array and you change that array in place. And that one, you don't need to know about the NumPy where. You can do it with slices. I think that's, well, I'll just point out the differences. So this is is this the whole thing? Many step in place? Kind of looks like a one step. Predict many. Oh yeah, predict many for one step, but do it in place. Yeah. So some parts of this are entirely the same. Although here we have already applied the selection that we're only interested in the array indices with children. When we pick out the features, thresholds, left and right indices, we can do the choosing left for just the ones that have children. And here, change the right indices. We're changing in place. Okay, this is a new thing. The way to do this in place, without NumPy where, is to first apply the step, assuming that everybody's going to go to the right, and then change the ones for which that is wrong. The ones that are actually not going right, they are in this Boolean array selecting from the right from this right indices array. And we are overwriting those values with the ones that actually do go left. So that's a way you can do this without NumPy where, but changing things in place is to first assume they'll all go one way and then change the ones for which that was wrong. And then do this to the very small set of values. It does the right thing. Wrapping it up into a predict many is just, it's the same way. We just do a for loop 100 times. Yep, there, 100 times, 10 times. The brain, okay. Right. We get the same results, and we can make a plot from that. Now, so those are two solutions to this. In this notebook, we go a little further to say, okay, so if we have all these different multiple solutions, which one is better? And better can mean different things. It can mean clarity. It can sometimes also mean speed. So this is kind of, I did this out of curiosity, and the results are interesting. What I'll do is I'll evaluate the rest of the notebook and then talk over it while it's computing computing those results. Where do I start? Performance comparison. So first there is the scalar in Python, which we know is going to be the slowest. Still working on that. There. And then when it gets the results, we'll see these all in a plot. I'll just collect them all into a plot. We can do a single tree traversal, you know, the computer science class thing, but we can compile it, and that'll make a difference. So this uses NumPy to do this imperative program of walking down a tree. So this is a single, predict single, and then you do it in a loop over all the elements. So then this is doing the thing where we've got all this data, this big array of data, and for each element, we walk down the tree. And the second element, we walk down the tree. Third element, we walk down the tree. This is how I would probably write it just straight off the bat. I would say, yeah, this is the straightforward way to walk down a tree. I'm going to compile it because I'm going to be running it many times. Yeah. And then to predict many, you just have to do a for loop over all the elements in the array. And the important thing is to get this for loop inside the part that NumPy compiles. NumPy compiles it if the function is decorated. It made the right plot. And there's some timing results. We'll see all the timing results at the end. Compiled array-oriented traversal. So I've been talking about NumPy and JAX because these are two ways to compile Python code. NumPy compiles imperative Python code. It takes your Python code, looks at the byte code instructions, and then replaces those with LLVM. So it's basically take this Python function, make it like a C function, and compile it and run it. JAX does a different thing. It has an array-oriented interface. In fact, you can only express immutable array-oriented algorithms with it. So the predict many in JAX is, it looks a lot like the NumPy solution. And when you get down to it, the results, drum roll. Here, the horizontal axis is time to evaluate. So we want to be on the left. Smaller is better. This is how long it takes to run Python for loops. Vectorizing it with NumPy, we get, orders of magnitude. This is the immutable version, and this is the in-place changing version. In-place changing is a little bit faster, but not so much that it matters too much. Even the in-place modification is still making a lot of intermediate arrays. Actually compiling it gets you even further because you're not making all these intermediate arrays and copying a lot of data. But then this is kind of interesting that by expressing it in an array-oriented form and letting JAX compile it, JAX happened to have solved this problem several times faster than an imperative problem. Like if you took this NumPy code and really wrote that Python code in C code, compiled that C function, it would be this fast. The JAX managed to find some, maybe it's about sequential walking over arrays in memory so that they don't fall out of CPU cache or something like that. I actually don't know what the difference is between these, but there's room for, by expressing it as an array-oriented way, you're saying less, you're not requiring it to do a for loop from the beginning to the end. And maybe it's taking advantage of that, maybe it's doing some loop unrolling, I'm throwing a lot of performance optimization words out there because I don't actually know why it's faster, but there's all these things that could be contributing to it. So sometimes that happens. Sometimes, even though this is the straightforward solution and it's compiled, it can do better by actually writing array-oriented code.
Is there no way to do like a verbose version of it to see what it's actually doing?
It expands out to XND. Yeah. So if you can read XND, and then it does further optimizations from there. So, no, not really. One thing you do have to be careful with is parallel processing. Jack's implicitly parallel processing, so you can sometimes find yourself comparing a single-threaded to a multi-threaded, but even accounting for that, I think I multi-threaded the number. Okay, so questions or moving on? Because now we're going to do something very different. Okay. A reminder, you probably now want to close these tabs and shut down the kernels. You have to do that explicitly, otherwise they all stay open and use up RAM. And we're going to move on to part 3. We're going to, okay, here's the slides, here's the workbook. The workbook is not quite empty, but it's not a huge number of things. Okay. I think I have one Quizlet in this whole thing. We are escaping the cube. So now we're going to be talking about array-oriented programming on arbitrary data structures. So far, oh wait, do I have to wait? We don't have a break or anything, do we? Nope, we just go right into it. Okay. So far, all the arrays we've dealt with have been rectangular or rectilinear. In 1 dimension, 2 dimension, however many dimensions, it's still some kind of rectangle. It could be small or large, some rectangles. But what if we had data like this? So think of any scientific problems that you might have run into where maybe within each group of whatever, you have different numbers of things. This is a ragged array or a jagged array. Both words can be used for that. Or what if you had data like this? This comes from some, like an art program, like SVG graphics turned into JSON, where you've got numerical stuff that you'd like to apply some numerical algorithms to in an array-oriented way. But this is coming in a structure that not only has variable lengths, because these are polygons which could be short or long, but also it's embedded in something where you've got meaning like x values and y values. Or what if you had data like this, where it's not even very numerical at all? Maybe you still want to do some kind of array-oriented programming on this. So it might be possible to turn the I think Dr. Codd's theorems on SQL. It's always possible to turn these data sets into tabular form by introducing a lot of surrogate keys. So database normalization. Here's where I'm going to wave my hands again. Database normalization. You can take this complex data and turn it into 20 different tables, and the tables have indices that point into other tables, and that all can be done. It could be inconvenient or less efficient in that form, depending on what you want to do. And they were likely given in this ragged or untidy form. Another word for turning everything into tables is tidy data, so in case you see that. So just saying that the data analysis starts after data cleaning is pretty naive, I think. Data cleaning is an important step. We should give it its due. So, we could deal with these data sets as JSON or as Python objects. And it's inefficient for the same reasons as for lists of numbers. So what we want is, both worlds. We want arbitrary data structures and array-oriented interface and performance. There are libraries. This is actually, I would say, a relatively recent field, because I don't think any of these libraries are certainly not more than 10 years old. Don't think many of them, I'd have to think back if it's been 5 years yet. This Arrow, Apache Arrow, this is an in-memory format and an ecosystem of tools. The way I would describe it, there's this Arrow ecosystem. They have the Arrow format, and they've got a bunch of different tools from this. It looks to me like they wanted to produce a database, but they didn't want to make it all one tidy package that you have to buy or whatever. They made this exploded database with all these tools. Each one of these tools is doing one part of it. So it's good for, it's especially good, this Arrow format is especially good for getting data between different processes. You can have a lot of processes on your computer all sharing memory and looking at the same Arrow array. There's awkward array, which full disclosure I'm developer for, and we'll be doing exercises on awkward arrays. This differs from Arrow in that it's for array-oriented programming like NumPy. It's trying to reproduce a NumPy-like interface as much as possible. But it's also losslessly zero-copy convertible to Arrow and Parquet, so it's not locking you into this different thing. If you have an Arrow array, you can turn it into an awkward array, and vice versa. And then Parquet is a disk format for storing large data sets that are columnar, stored like an array, where the value, like all the X values are all next to each other in memory and on disk. And that helps with compression and things. But they're also arbitrary data structures. And you can use that, if all the X's are next to each other on disk and all the Y's are next to each other on disk and they're separately compressed, you can get just the X values without reading the Y values. That's a very useful thing. So let's look at Arrow. There's a PyArrow, which I think is maybe the most used language for it. Arrow is a multi-language project. There are base implementations in C++ that are exposed through Python to PyArrow. But since this is supposed to be for sharing arrays between processes, there's Julia bindings and Fortran bindings and all the things. So here's an Arrow array. This is what the data type looks like. Okay, it's a list. And then within that, the lists have items that are structs, like records. That the X has type double, the Y has type list of ints. And when it prints out on the screen, it prints like this, which is, it's designed to be a backend. This is what library developers want to see in order to glue Arrow arrays into some kind of project. This is not what I would want to do data analysis on. So here I'm describing the distinction between Arrow and awkward array. Because awkward array is meant for just doing data analysis directly on. So here I'm going to pull the array from Arrow. The Jupyter representation and the in Python prompt representation are a little bit different. Jupyter is more expanded for doing interactive data analysis. It shows you the contents with a ... if there's not enough room. And here's the data type. So the type is described using a language called a language for describing types of arrays of data structure called data shape. And that says got an array of length 3. It contains variable length lists. And then these lists are optional records. Optional means it could be none, could be missing. A lot of data from Arrow could be missing. The X could be missing or could be a float. The y could be missing. Option is question mark spelled out, which is a list of integers. When we make awkward arrays directly and not coming from arrow, there will be a lot less options, a lot less option type. So rated to Parquet, and looking at some Parquet metadata, and then we can just read it back from Parquet. And this is the awkward from Parquet to Parquet, for saving these arrays. So back to those data sets, like the what if. What if you had this kind of data? What if you had that kind of data? What if you had this other kind of data? These are implicitly using a from iterator to turn Python objects into awkward arrays. But there's a ragged array. We just read that into an array. And we can do multidimensional indexing. So for the third element of the array, that's a list, take its 1th element. I think that's another list. Take its last element. That's another list, because this is a pretty deep ragged array. And then take the 2th, whatever. And then you get down to a value. So I could do this in pieces. Like that. Now we're getting deeper into it. Now we're getting deeper into it. And then that's all the way down. So, and then basic slicing. From 1 onward, from 1 to 3. And this is for each of the ragged components. And then advanced slicing, where you are using arrays of Booleans, or arrays of integers, along with positions and such. So, doing all the things. All these things that you can do in NumPy, and is just extending it to, well, what if the array is ragged? And in particular, making arrays of Booleans, and this happens to be a ragged array of Booleans, you can use them to select items. So here I'm just selecting all the positive ones. And this is, this is the syntax you would use in NumPy. Reductions, sum at axis equals at different axes. So sum at the deepest axis, -1. That's usually the one that you want. But the NumPy default is axis equals none, so that will sum over everything. Axis is 0 is cutting it a different way. Remember the picture that I made? I don't know if this is on the next page slide. It is. Oh. Yes.
It just says none, right?
Yeah, that says none. Yeah. Okay, I got to fix this picture. Because it looks right on another screen anyway. So we make this small ragged array, which is the same as this up here. 1, 2, 4. This next one is all blank, because it's, it has length 0. This next one, I made an option type. So put in none, 8, and then leave that blank. And then this last one is just 16. So there they are, in a raggedness. And axis 0 is adding this way. Axis 1 is adding that way. Just like with a NumPy array. And just the pro tip is almost always want axis -1, the deepest. So when in doubt, start there. The structured, this has those nested data structures. And we can do formulas. We can take the structured array, select from the points, the points field of the outermost record, the x field of the inner record, square it, do the same thing for y in order to compute distances. So then if we had this data, this JSON blob that has all these positions, and GeoJSON comes to mind, where you have latitude and longitude, we can do math on them now, even though they are variable length polygons. Difference between the top and bottom is here, selecting fields is like doing a slice, picking a string. The string is the name of the field, so it's part of the slice syntax. NumPy structured arrays work this way too. And here we do it with dots, which would be more familiar to people from Pandas. Yeah?
What does the type 6 times var times 64 mean?
Yep. This array has length 6. There's 6 things in it at the topmost level. Then the second level are variable length lists. Oops. And then the third level is floating point numbers.
So is there a constraint that all the data should be of a particular type? Can I mix in like strings and other kind of stuff?
Yeah.
So
And
then it will become an object?
then it becomes union. Yeah. And if you do that, you'll find that some operations, some things you just can't do with unions. Like you can pass awkward arrays into NumPy and have NumPy iterate over these things unless they're unions, because then NumPy can't type them, you know. So if you're starting from GeoJSON, you will get unions because it does mix polygons with plain points with polygons with all these things. They all go into a single place. So you get unions, and then you would want to do some awkward operations in order to split them out and get all the polygons in one array, all the points in another array, and stuff like that, and then be able to work with them. So this is kind of data cleaning might be much of what we're using awkward for. Okay, so we're going to have a Quizlet. It'll be the only one before we move on to the last project. We're going to be given this data set. These are movies by Sam Raimi. And we want to select the movies that do not contain Bruce Campbell, because Bruce Campbell was in an awful lot of Sam Raimi movies. Not all of them, no. In fact, I had to search to find some that he wasn't in so that this would be a non-trivial. Okay, and for your reference, there's, for your reference, there's awk.all, awk.any, numpy.inverts, awk.num. There are actually quite a few different ways to do this using different functions. Okay, so it's been a little bit more than 5 minutes, and we're a little bit more than half and half. So I'll go through this, and then there'll be more chance to practice on in the projects, which, like I said, it doesn't. It's not a hard problem. It's just a new context of doing these things on arbitrary data structures. So. Answer is first, let me put parentheses around this. Data actors, we'll see, when is this equal to Bruce Campbell? Maybe before even this, data actors, what does that look like? It's pulled just the actor field out of those records. And then by saying, when is it equal to Bruce Campbell, this one string broadcasts to all of these other strings, where I'm using broadcast in the NumPy sense. This equals is going to do an array operation, give us an array of Booleans, which is true for every actor that is equal to Bruce Campbell and false for everyone that isn't. So there we go. So we have trues and falses. Now, this is an array, and we want to know in each one of these lists, because there's one list per movie. It's a quick reminder what the data looks like. Each movie has a list of actors. So each one of these lists is for a movie. For a movie, we want to ask, are they all not Bruce Campbell? And this axis 1 is the deepest, so I'll be more clear about it in saying axis -1, counting from the bottom up. So now the question, all not Bruce Campbell, is answered false, because there's a Bruce Campbell in there. False, false, but then this one, which I think you said it was a simple plan, he wasn't in it. So, so this is the first one for which, the first list that doesn't satisfy the criteria. So there's a true there. And then also on this last one. So then now that we have these Booleans, we can reapply it to the original data and slice the data so that we get something that has the same data type as the original data, but it has just selected the ones that, pass this Boolean. So that was, that was putting together several of these NumPy concepts, but doing them in, on structured data. Yep. So then there's the project, which we want to start it in 3 minutes, and then we'll be perfectly on time. Yeah.
Can you explain the axis -1 one more time?
Oh, yeah, sure.
Understand, but without that, just one single value.
Shoot.
Okay, the equation.
It's back here. The way that NumPy numbers the axes is the outermost is axis 0, the next in is 1, 2, 3, 4, whatever. And the innermost is -1, outside of this -2, -3, -4. So it's just like how Python likes to, use positive numbers to count forward and negative numbers to count backward. And so then it just becomes this, so in a two-dimensional array where you have axis 0 and axis 1, you could also call it axis -1 and axis -2. It's just, this happens to be the case that in these kinds of problems, you'll almost always want to reduce this way across the variable length objects. Then you do want to reduce this way. Reducing this way is odd. It's a strange thing to do. Yeah. So it's almost always -1. Now, this last topic is not used in the project, but I just want to show that you can actually do quite a bit of the things that you would do in imperative programming with for loops over variable length structures in this paradigm. We're not limited to only things that are very formula-like. And we do it by just introducing some primitives that NumPy doesn't have, because these things only make sense in the irregular context. Things like taking a Cartesian product, maybe element by element, so that here we've got, in the first array, 3 things, 0 things, 1 thing, and in the second array, 2 things, 1 thing, 2 things. And we want to get an output array that has all combinations of yellow and magenta. There's 6 ways to put these 3 and these 2 together. Nothing here, because there's no ways to put it together nothing in 1. And then 2 ways here, because this yellow goes with the first, yellow goes with the second. So this replaces imperative double-nested for loops. Yeah, and you can do Cartesian products. Actually, this is just like itertools.product. So if you're familiar with Python's standard library, itertools, this does what itertools.product does on arbitrary many arrays, and it does it in a vectorized way. And then octa-combinations takes one array and finds all combinations within it. So take these 4 things and find all the ways to pair up 2 of them. There's 6 ways to do that. Or nothing, you get nothing. And if you got 2 things, what are the ways to pair up 2, and there's only, I guess there's forward and backward there. This is just like itertools.combinations. The similarity in name is intentional. Okay. So an example with our Cartesian, given some letters and numbers, this is what it does, just to see it in a concrete example, and small example. You got 1, 2, 3, and AB. You get pairs of 1A, 1B, 2A, 2B, 3A, 3B. Yeah, because you got 1, 1, 2, 2, 3, 3. AB, 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 AB. And it has now made a new data structure, a tuple, which is like a record with no field names. For combinations, 1.1, 2.2, 3.3, 4.4, we get the pairs that don't repeat. So this is what you would use to replace a double nested for loop where the second for loop only goes over, different values from the first. So if you've got something that's kind of like, think of it a grid, and you want to get all pairs in that grid, you'd use Cartesian product. If you want to get like the upper triangular, use combinations. So let's use this as an example. Which actors in the same movie have names that are the same length? Kind of a weird question to ask, but this is using combinations. So first we make actor pairs by taking those actors and make length 2 pairs. Gamble, this pulls this 0 in quotes. I said this is a tuple. It's like a record without field names. The name of this field is quote 0. And the name of this field is quote 1. So that's where that's coming from. So actor pairs 0, we're getting just the lefts of these. We did actor pairs 1. We get just the rights of those. Num of actor pair 0, now we're getting the lengths of these strings. Num is a function for getting lengths of variable length things. And then finally we have this expression. Num of the left parts of the pairs, num of the right parts of the pairs, where they equal, select, and then we've got different actors whose names are the same length. A weird question to ask, but we can do these things by having combinatorial primitives. So let's go to the project. Here we are, project and solutions. We're in part 3. It's a data set of Chicago taxis. I'll let you read it. But they're driving all over the place, all over Chicago, and they're making these polylines, and each polyline has a different length. And there's a lot of data. So the thing about this example that's different from the others is that this is using a moderately large data set. The full data set is some, dozens of gigabytes. And this is, and I think we're pulling just the first bit of it, so maybe as much as a gigabyte or something. Something you definitely don't want to do Python for loops over. But they're variable length, so we need it. This is pretty much until the end. So it's 11:30. Okay, we're only 5 minutes late. Check that out. So we'll be doing this project. Again, these are results. Tell me how you're doing. And this is it. Do this project. We'll have a break, and then we'll talk about solutions. Oh yeah, absolutely. Xarray is rectilinear, so it's another Rubik's cube. Right. But it has rich metadata on everything, on every axis, and you know. So xarray, you can do the dot syntax for picking columns and things, and all of those columns have units and documentation and all those things. But it is completely rectilinear, and we've had quite a few discussions about can we merge, you know, can we get xarray and awkward array together? It seems like we can't because it really is, you know, a NumPy-like structure, yeah.
So awkward array would be like if you didn't have rich metadata and you just had data.
Right, so now we've got a Venn diagram.
Yeah.
You know, we've got arbitrary data structures, and then there's rich metadata. Right, that. We're doing some things to add more metadata into awkward array. Not to take xarray's place by any means, but just to be able to preserve some of that information if let's say you get untidy data and you use awkward array in order to tidyify it, you know, making analysis relevant decisions to get it down into something rectilinear, and then you want the metadata from the initial file to pass through into the xarray.
Gotcha.
That's why we want, but we're still in the process of adding that metadata to
So
awkward.
my other question would be, I noticed in the README for awkward array that it does a very efficient memory footprint. How does it do that?
The same way that Arrow and Parquet do it, actually.
Really?
Yeah, so there's, and this is why this is all kind of recent, is because there's some new algorithms for doing that.
Right.
So conceptually, the data is a big array of a lot of little trees. It's possible to rearrange that into one tree where there's a big array at each node. So the one tree takes the place of a bunch of little trees.
Gotcha.
Yeah.
That makes
And then it's, you know, it's just working sideways to think of the indices into these things.
Cool. Thank
Yeah,
you.
sure. Yeah. So an awkward array is actually a whole lot of buffers. And that's why it doesn't fit with xarray, because an xarray is one buffer. So. Yeah, and do, you know, pair up again and talk with each other.
Question. So once the awkward array is created, can I add more elements to it? Can I only change?
Yeah, right. Awkward arrays are almost immutable. Almost, because managing this complex many buffers would get out of hand if you could change individual elements. It's technically possible to change individual elements, but you have to get into like hacker mode to do that. From an ordinary data analysis perspective, you can add new columns at any time. So if you have these records, kind of like the movie names, actor, you know, list of names, at each one of those record types that has fields, you can add a new field with more elements. And you can do that in place. Well, it appears to be in place for the top level object because it's actually just putting another buffer into its list. But the underlying things, the underlying buffers are all immutable, unless you hack it. Relief. So let me get over to that. Okay, so actually, just as a show of hands, people made it to the exercise part of this. I want to get feedback on knowing if the preamble was too long. Everybody was working on the, did anybody not get to the part that says the exercise? Okay, good, yeah, so preamble's not too long. All right, so, so then a few of you have solved it. Yeah. But maybe most haven't. So you're working on this exercise where the goal is to calculate the length of each path. The length of a path is the sum of segment lengths. So this is just like the first quickie, except the first quick quiz was only doing this for a single path. And now this is doing it for lots of paths, and it's like a ragged array of paths or something. So that's where the difference is. Let me go to the solution notebook. It brings in all the imports, loads up the data. Yep. The preamble things of converting longitude and latitude into kilometers. Because if we're calculating distances, we can't do that in longitude and latitude. The longitude means a different length than the latitude. Simple path example for comparison. Using this awesome fact that Python variable names can have Unicode as long as it's a letter. So the solution. Okay. Maybe I need to go a little bit smaller, or I could break this up into multiple lines. Into the square roots of that. That's where the square root ends. Yeah. So here's the solution. The distances, and it's actually one line. So you can do it on multiple lines, but the solution could be expressed on one line. The paths are 3 axes deep in all of this. You have to go through the set of all, what was it, all taxis, and then the set of all trips. I think there's one more in there. But there was, there's a lot of structure in this, and so you have to go 3 levels deep before you get to the actual paths. And then when you're acting on the paths, you can do this trick of slice off the first one, slice off the last one in each path to get, to be able to do the, I'd love to pull up that graphic again, but instead of comparing nodes this way, compare them this way, that graphic. We're doing that for each path, though. So this relies on the fact that these 2 outer levels of structure have all the same lengths, which they do because we're pulling it from the same thing, this kilometers east and kilometers east. They all have the same lengths all the way down. They're variable lengths, but kilometers east has the same lengths as kilometers east, all the way down to this last, including this last level, because we slice off one at one end and one at the other end. So they all have the same lengths all the way down. And if you were getting a lot of errors with, couldn't slice something or other, it's very easy when you have ragged data to have those lengths not match. It's easier than when it's regular. When it's regular, you can get mismatched indices. But when it's irregular, it's even easier to get mismatched indices, which is good because if you have mismatched indices, you're computing something you don't want. So it's good that it stops you. So then this is doing the delta x in all those paths. This is doing the delta y. And from there upward, square, sum, square root, and then a summation. Actually, I should actually evaluate this. Here we go. Summation at axis equals -1 because it's these paths, the deepest. Yeah?
What does HSM bring that NumPy sum doesn't?
Nothing. We had to re-implement sum, naturally, because it's operating on awkward arrays instead of operating on NumPy arrays. And we use NumPy's NEP18 dispatch mechanism to say, if you have NumPy sum on awkward array stuff, switch over to the awk.sum and do that. Yep. Right. So then the type of this is there are 353 variable length, possibly missing numbers. I can't remember why the numbers are possibly missing, but okay. There they are. And here's one of them. And somewhere there's, you can compare this to the pure Python solution. They are the same. And then if you went beyond the first thing, there's other problems within this notebook, but I'm not going to go into them because I don't think people got into those bonus problems. All right, so that is the end of it. Have a great lunch. Have a great conference.